Lesson 6.3 is all about how do we add and subtract radicals. We still have to be able to multiply and divide radicals. In fact, we're still going to be doing a decent amount of multiplying radicals here. But the big thing is now, how do we add and subtract those radicals? So, notice what it says up there. And I know that R is kind of blotched out there by the hole punch, but radicals must be like terms in order to add and subtract the coefficients. So when we talk about like terms, for instance, in order to add 3x and 5x, can I add 3x and 5x? Yeah, 3x plus 5x is 8x. So that does work. However, can I add 2x and 7y? No, 2x plus 7y is 2x plus 7y. So we're talking about like terms, we're talking about something like that. That they have to have, with variables, they have to have the same variable. X's add with x's, y's add with y's. With radicals, like terms means you're not just adding a square root to a square root, it's specifically square root of x and square root of x, or square root of y and square root of y. We can't add a square root and a cube root, and we can't add square root of x to square root of y. They have to be identical radicals. So you'll like this first section. Very easy and to the point. And so as we look at example A, thoughts on 3 square root of 5x minus 2 square root of 5x. What's your guess, Lorna? Half right. It all comes down to how we write our final answer. So if you do that, are you saying the answer is just 1?
I don't know.
You don't know how you're going to write your final answer yet. Okay, fair enough. Okay, so first of all, can I subtract these? Is the radical part identical? Square root of 5x, square root of 5x, yes?
Yes.
So my question is, what is 3 of something minus 2 of something? 1 of something. So I like Lorna's 3 minus 2 because we are subtracting, those are like the coefficients. The square root of 5x is like your x or your y. It's your variable piece that just stays along for the ride. Depending on, and I'm not saying you have to do this, but one way to write this would say, okay, I'm doing 3 minus 2, the pieces out front, and then I'm going to multiply by square root of 5x. That's the gist of what I'm doing. We all know that 3 minus 2 is 1. And so then this is 1 times the square root of 5x. But what are you going to guess? Am I going to write 1 square root of 5x as a final answer? No, it's just like, do we usually write 1x as a final answer? No, you don't have to write 1 as a coefficient. So in this case, I'm just going to write square root of 5x. So the idea that if you have no number in front of a radical, realize there's always that invisible 1 that matters. Okay? Lorna?
It doesn't matter that there's 2 square roots of 5x's. It just say 1.
Well, there's really what there is there's 3 square root of 5x's, and we're taking away 2 of them.
Right. Yeah.
So now you're left with 1 when we have 3 and we take away 2. It looks really confusing, but in all honesty, this is like, when did you guys learn subtraction? First grade? I don't know. I'm guesstimating there. It's really kind of like first grade subtraction. 3 minus 2 is 1. It's just that now we have that algebra piece tagged on. Okay? And I gotta get you guys to not overthink this. That's what I have to get you to do. Ready to try B? Okay. 6x squared, square root of 7, plus 4x, square root of 5. Thoughts? Say what?
You add your square root of 6, then you add them together.
Not exactly. And what you guys trying? So far, you're the only one that's tried. No one else is saying anything. Not sure why no one else is saying anything here. Lorna?
We'll just do 6x squared plus 4x and then add the radicals of 7 and 5.
No. Kylie?
Wouldn't you just multiply the radicals? Because those aren't like terms because it has the x squared.
Yeah, the x's aren't the same.
Okay. Well, it's not even so much that the x's aren't the same. Emma?
Do you have to like take the square root of 6x squared to be able to add 4x?
No. You guys are way overthinking this. What does it want us to do here? It wants us to add, yes?
Just that.
Okay. That's all it wants us to do is add them. The question is, can I add them?
No,
Okay.
they're not like terms.
Okay. See, you guys were afraid to say that, weren't you?
Yeah.
Here's the deal. If we can add them, they must be like terms. Are square root of 7 and square root of 5 like radicals? No. Square root of 7 and square root of 5 are my radicals. They are not the same, so I cannot add them. We're not even going to talk about the 6x squared and 4x issue because we didn't even get to that. Okay, that's a whole nother issue. We didn't get there. Don't worry about it right now. What I'm stuck on is square root of 7, square root of 5, not like radicals. So guess what? These cannot be combined. And the math teacher can't spell. There we go. Now, depending on how Math Excel asks it, you might be able to pick cannot be combined. Or you might just add. What are these when you add them together? It's just same exact statement, just rewritten. Okay? And why was this that I could not combine this? And this is because the radicands, if you remember, those are the numbers under the radicals. Radicands are not the same. So all because that silly little 7 and 5 are not the same. Okay, we ready for C?
Sure.
12 cube root 7xy minus 8 cube root 7xy. Guesses? I'll call them just that right now since we're still learning.
Yeah.
Jocelyn?
You take 12 cubed minus 8 cubed, and then you do the same thing you did on the first one.
Okay, except those threes aren't on the 12 and 8. Those are cube roots. Otherwise, I think I would agree with you.
What did you say, 12 minus 8?
Yeah. 12 minus 8 is 4. And then what am I going to put with that 4?
Cube root of 7.
Cube root of 7xy. Okay? So I see what Jocelyn was misreading there. She saw it more as 12 cubed times the square root of 7xy minus 8 cubed times the square root of 7xy. But here's the deal. Are my radicals the same? Yes, the radicals are the same. They're both a cube root and a 7xy. So then you're just taking your coefficients out front. 12 minus 8 is 4. Was that one a little bit better? Less confusion there? Okay, D. 7 cube root of 5 minus 4 square root of 5. What are our thoughts there? Justin?
They can't combine
Why not?
because you have a cube root of 5 and a square root of 5.
Ah, this guy is a cube root. This guy has the invisible 2 for a square root. Does it matter that they were both 5s under the radicals? Not when we have different roots. Okay, so this, just like B, we're going to say cannot be combined. Or if you have to actually subtract them, you just rewrite the original problem. Now, the difference this time, why could these not be combined? And I'm going to use the word indexes, or you could say the roots, but the indexes are different. Did we all catch that one? Okay, E. 3x square root of xy plus 4x square root of xy. What do you think, Emma?
7x times the square root of xy.
Easy enough? Is it getting easier as long as we don't overthink it? Okay, here's the deal. Square root of xy, square root of xy. Are they alike? Yeah, those are identical radicals. So then you're just adding the outside pieces. 3x plus 4x is 7x. So 7x times the square root of xy. And F. 17 times the fifth root of 3x squared minus 15 times the fifth root of 3x squared. Are we better on this one? Less guesswork, more we know what's going on now. Cam?
2 times.
Okay. They're like radicals, aren't they? 17 minus 15 is 2. So 2, and then you just keep the like radical. So fifth root 3x squared. Okay. Got the basic idea of what we're doing? Okay, moving along then. That's kind of our basic introduction. When can we add and subtract? When can we not add and subtract? Let's look at example 2. Let's look at this word problem. Okay. So, what's my first job in a word problem? Read it. Let's see what we're doing here. The following is a picture of a stained glass window made up of square pieces and portions of square pieces. If the side of each square measures 5 inches, find the perimeter of the window. Okay. So the following is a picture of a stained glass window. We find the perimeter. We're trying to find the perimeter of the entire thing, right? What do I mean perimeter? Yeah, distance around, basically, the short of it. Add all those sides up, right? Add all those sides up somehow or another. So we need to know some distances here, don't we? Okay. Now, what do we know? These are squares. No, obviously, they are squares that are turned on their corners, right? And so each side of the square, that's 5. That's 5. That's 5. Oops. Each of those little pieces are 5. And assume, I know picture's not perfect, right? But assume you're either looking at full squares or half squares. Does that make sense? Picture may not be drawn exactly like that, but. So, each of these sides or squares are 5. What do we need to know to be able to do this? If I draw that in right there, is that 5? What portion of the square is that? Or what? It's half of the square. And where does that piece get drawn in a square? If we think about a square, here's my attempt at a square. 5, 5, 5, 5. Where is this piece at? It's that diagonal there, isn't it? Is that 5 also? So if I tell you it's not 5, how do we find it? What do you know? Think about a square, guys. And think about where I just drew that, yes. We want to know the distance of that. I would call that the diagonal of the square.
A squared plus B squared equals C squared.
Oh, what is a squared plus b squared equals c squared? Pythagorean theorem that works when we have a right triangle. If that's a square, is that a right triangle? It is, isn't it? I feel like I drew my square a little low there. I don't really have a ton of room, but so yes, we're going to use a squared plus b squared equals c squared. Actually, you know what? I'm going to move that over to the left because I'm not going to have enough room to do what I need to do there. Okay. Hey guys, what do you remember about Pythagorean theorem? A and B are your okay, the sides, the legs of the right triangle. Is this coming back to us at all? How do I know which are A and B? They are the two sides that are the shortest. They also meet at the right angle. What's C? The hypotenuse. So C in this case is my question mark. It's the one that goes across the middle. So we're going to say 5 squared plus 5 squared equals c squared. 5 squared is 25. 25 plus 25 is c squared. But 25 plus 25 is 50. What do I do now to find c? If c squared equals 50, take the square root. So when I take the square root of c squared, I get c. And when I take the square root of 50, okay, well, I wrote square root of 50 for the moment. I'm not going to work with the decimal, just because, in Cam's word, it's a fun decimal. Meaning, it's not a nice, neat, like 1 or 2 digit decimal, is it? It's that long, messy, irrational type of number. So, I would like to simplify this. Yeah. Blue paper time. What perfect square is in 50? 50 has a 25 in it, doesn't it? Oh, wait, we still have to do that? Yes, we still have to be able to simplify. This is why I told you guys have the blue papers out today, right? They haven't gone away. So, if the square root of 50 is 25 times 2, the square root of 25 is 5. And the 2 stays under the radical. Right? That's what we learned last week. That's what I taught, what, Wednesday and Thursday? So what do we know now? This piece right here has a length of 5 square root of 2. What about this piece here? How long is this piece? 5 square root of 2. What about across the top? We have 5 square root of 2, 5 square root of 2, and 5 square root of 2. The good news is we only had to use the, all the squares are the same, right? Okay, so my question to you, how long and how wide is my window? This is what we've been learning today comes back into play. How long is this stained glass window? Okay? And so if we put that all together, it's 5 square root of 2 plus 5 square root of 2 plus 5 square root of 2, or 3 times that, which is going to be 15 square root of 2. Is how I would write that, because 5 plus 5 plus 5 is 15. Now with that knowledge under your belt, what's the width of this window? It's 5 square root of 2 plus 5 square root of 2, which is 10 square root of 2. How do you find the perimeter of this window, which was our whole goal? We said adding up all the sides, right? Some of you are probably sitting here thinking, oh, it's perimeter of a rectangle. I like to say 2L plus 2W. Can you do that?
Yeah.
Yes. Some of you are saying, oh, don't go fancy on me, Mrs. Sargent. Then fine. If you want to be very basic and don't go fancy, adding up the sides of the window. Length plus width plus width. Does it matter how you think about this?
Yeah.
No, you just have to know perimeter. You're adding up all those sides. So, 15 square root of 2 plus 15 square root of 2 plus 10 square root of 2 plus 10 square root of 2. What does that add up to be? Yeah, they're all square root of 2, so we can add them. 15 plus 15 plus 10 plus 10 is 50 square root of 2. Now, yes, we worked with the radicals. Could you give me a final decimal answer there?
Yes.
And what would that final decimal answer be?
70.7.
Okay, if we round it to one decimal place, I think that's rounded, isn't it? 70.7 what?
106.7812.
No, as in what's my label?
Inch.
Oh.
Inches. I'm like, she's giving me more numbers. What numbers? Oh, okay, no, I don't want the rest of the decimal. 70.7 inches. I think you have something, a problem like this idea in homework. I think is it a garden maybe or something? I don't remember exactly. But I think when you get to the end, they want a decimal. My recommendation, though, is don't jump to the decimal until you get to the end. Because otherwise, if you have to work with decimals throughout the time, it's really easy to make a mistake with all the decimals and everything. Now, as word problems go, I would like to think that one wasn't horrible, was it? We've definitely seen worse. Okay?
It could be worse.
Yeah, it could be worse.
It could be worse. We could be doing proofs.
This is not geometry. You won't be seeing proofs from me. Although I do have to do a little bit with proofs and pre-calc. So, there's a little bit there. Okay, example 3. The title kind of gives it away. Simplifying before adding or subtracting. Okay? What is the simplest form of each of the following? So as you look at A, square root of 12 plus square root of 75 minus square root of 3. What's the first thought that goes through your brain?
They're not the same.
They're not the same. So can I add them and subtract them? No. So if we go back up to the top section of when we were doing it, we just said cannot be combined, right? But here's the deal. Okay, we have to go with what we learned in 6.2. Notice I just picked up my blue paper. If we do a little simplifying work, can these possibly be added or subtracted?
Maybe.
Maybe. And here's my hint. Most likely, yes.
Darn it.
Okay? Usually you can simplify and they will magically work. And I say magically work, it's designed to work out most of the time. So, okay, one at a time here. Square root of 12. Grab your blue paper, not your calculator, your blue paper. I don't want to know a decimal answer, okay, because when we are saying simplest form, we are not going decimals. There's very little we do with decimals in this chapter. What do you know about square root of 12? Is it a perfect square?
It has a
Okay, it's not a perfect square, but it has a perfect square?
Yeah.
If I look at my blue paper, what does 12 divide by? 4. Okay, so you remember how to do this? I'm going to rewrite 12 as the square root
4 times 3.
of 4 times 3. Are we getting a grasp on that? I looked for 12. It divided by 4. My calculator told me if I don't remember. Now, while we're here, what do you know about the square root of 4? It's 2. And so where do I put that 2?
Outside.
Outside the radical. So I have a 2 outside, and then we have a
3.
square root of 3. Okay, that's that one. And that's what I would do on this, is I would just kind of treat them one at a time. Now, look at your middle one. Square root of 75. So I'm going to take my blue paper again. Is 75 on my list? Is it a perfect square?
No.
No, it's not. So now I'm going to grab my calculator. I'm going to start checking. What is the largest perfect square that 75 divides by? Are we finding 25? So, underneath my square root, I'm going to write 25 times 3. But what is the square root of 75? I mean 25, yes.
5.
The square root of 25 is 5, and the 3 stays under the square root. Okay, got one more to work with. Square root of 3. Is it a perfect square? Are there perfect squares inside of it?
No, so it just drops down.
But does it matter? Because it just so happens, what's good about the square root of 3?
The others are square root.
Oh, the others ended up being square root of 3 also. I say magic, but again, it's the problem that's designed to work out that way. 9 times out of 10, your problems will work out like this, where notice square root of 3, square root of 3, square root of 3. They are all like radicals. So don't stop here. What is 2 square root of 3 plus 5 square root of 3 minus square root of 3?
6
Six
square root of 3.
Do we all agree with that?
I put 8.
Well, the last one is a minus.
That's a 2.
Okay, maybe there's a mistake.
7. 7 minus 1 is 6.
Okay, so we're all okay with 6. And the reason I ask is I was waiting for someone to tell me the answer to this was 7 square root of 3. Or to tell me the answer is 7. Why is it 6 square root of 3? Well, 2 square root of 3 plus 5 square root of 3 is indeed 7 square root of 3. What's the invisible number here that's not showing?
1.
If there is nothing else in front of a radical, there's always an invisible 1. So 2 plus 5 is 7, minus 1 is 6. And so I do agree with 6 square root of 3. If you made that mistake in your head, no one said out loud, so made that mistake, though, learn from it here. Do we follow that? Yes and no? Okay, let's look at B. Cube root of 250 plus cube root of 54 minus cube root of 16. Can I add and subtract these as is? No. Okay, hardest part of this problem in my thoughts, I have to switch my square root brain out for my cube root brain. So go to that middle column on your blue paper. It is so easy to forget to switch columns. Okay? Sorry, I'm not laughing.
You are.
Okay, I'm laughing with you, though. I'm laughing with you. As Elena is over there erasing her paper, smiling at me like, I might not have made that mistake. I didn't make that mistake. No, not at all. Okay. But here's the deal. You're going to get these mistakes out of the way today on the notes, so you don't have to make them on the homework, or on the quiz, or the test. Perfect. See, perfect time to make the mistakes. Okay. Cube root of 250. Is cube root of 250 in my middle column here? It is not. It is not a perfect cube. But guess what? It probably divides by something.
It does.
So 250. Does it divide by 216? No, I get a decimal. Does it divide by 125?
Yes.
Oh, it does. So that is 125 times 2. Okay, I'm going to go ahead and simplify this while I'm here. Whoops. What is the cube root of 125?
5.
According to my paper, it's 5. What is the cube root of 2? Cube root of 2. What's this means probably going to happen? The rest of these are probably going to have a 2 left over in that cube root, aren't they? Which can actually work to your advantage if you let it. Okay, so now I'm going to say plus cube root of 54. Well, you can do this one of 2 ways. 54 is not on my list. I can start looking, there's not many choices, and seeing what 54 divides by. Or if I want, I could take 54 and divide it by 2, since that's what's left here, and see if that happens to give me a perfect cube. Does that make sense the way I say that? That's a good shortcut if you understand that. So, what does 54 divide by that's important? 27 and 2. So this is a cube root of 27 times 2. What is the cube root of 27? 3 times the cube root of 2 minus, can I do the cube root of 16? No. There's only one thing to check though, isn't there? Does 16 divide by 8? It does. So 16 is 8 times 2. What is the cube root of 8? 2. And then we leave the other 2 under the cube root. Okay. What I called magic earlier? Just so worked out that, do these all have matching radicals? Yeah. 5 cube root of 2 plus 3 cube root of 2 minus 2 cube root of 2. Is what?
6.
6 cube root of 2. 5 plus 3 is 8. Minus 2 is 6 cube root of 2. And you're remembering to put that little cube in there, yes? Because Math Excel will count you wrong if you forget that cube, won't it? I'm sure you've done that at some point in time or another. So, unfortunately, if you don't write that little cube on a quiz or a test for me, I have to take off. I don't take off much, but I do have to take off something. So, okay, where are we at on time? Okay. Well, we can go ahead and look on the back and talk about it a little bit, and maybe get that first example done. Example 4. I know today's whole lesson is supposed to be about adding and subtracting, but there's a lot of pieces that go into a lot of places where adding and subtracting matters. So example 4 is multiplying binomial radical expressions. So basically multiplying when there's 2 terms in a parenthesis times 2 terms in another parenthesis. So what is the product of each radical expression? Well, when you look at A, 4 plus 2 square root of 2 times 5 plus 4 square root of 2. What's a process you know here? FOIL. Some of you are going to say distribute, right? It's not that you have to know this as FOIL, but what I tend to say here is FOIL. Because when I say FOIL, that jogs a lot of your memories, doesn't it? If I just say distribute, maybe not so much. So when you see 2 times 2, we are foiling or distributing. So let's go ahead and do this A. So first means I'm doing first term in the first parenthesis times first term in the second parenthesis. It's your first. What's 4 times 5? 20. That was easy enough. Okay. Oh, that is my outsides. So 4 times 4 square root of 2. It's your outside terms. What is 4 times 4 square root of 2?
16 square root.
Okay. Multiply the whole numbers. 4 times 4. And then just keep the square root of 2. So 16 square root of 2. Now we're going to do our insides. So now, 2 square root of 2 times 5.
10 squared.
Okay. Whole number 5 times that 2 outside is going to be 10. And you keep the square root of 2. So 10 square root of 2. And then I'm going to do last. The last term in each parenthesis. So now I'm doing 2 square root of 2 times 4 square root of 2. So this is where whole numbers with whole numbers, radicals with radicals. What are my whole numbers here? 2 times 4 is 8. Square root of 2 times square root of 2. Square root of?
It's just 2.
Okay. I wrote square root of 4 for the moment. But can we also say square root of 2 times square root of 2 is 2? You can't. Square root of smiley face times square root of smiley face is smiley face. It's exactly that. Okay? Now, here's the question. Am I done? No. Always after you FOIL, you have to clean up your like terms. So let's see what I can clean up here. What's the obvious cleanup? Can I add 16 square root of 2 plus 10 square root of 2?
Yes.
Yes, I definitely can. 16 square root of 2 plus 10 square root of 2 is 26 square root of 2. Now, this 20 right now, it's just a whole number. I'm just going to carry it down. What's the catch with 8 square root of 4? Or some of you have 8 times 2.
Yeah, 8 times
Yeah, the square root of 4 is
2.
2. So this is really 8 times 2, which is 16. Am I done?
Now you can add your whole numbers together.
Okay. Almost, right? 20 and 16 are whole numbers. Add them. 20 plus 16 is 36. Plus, what else do I have?
26, 32.
26 square root of 2. What is 36 plus 26 square root of 2?
62 square root of 2.
Nope.
36 plus 26, 32.
Our final answer.
Because there is no square.
Can I add those? No, because they are not
Like,
like terms. One of them has a square root of 2. The other does not have a square root of 2. Okay. You are welcome to get started in the homework tonight if you want. However, more by priority for some of you, make sure 6.2 review is done. If you didn't get 6.2 done last week, get those caught up before you jump into 6.3. Okay? So make sure you're getting caught up on everything. And we will continue notes in 6.3 tomorrow.